All right. So I think we can start from where we left off yesterday. So if you remember, we introduced this generic interface describing what a monoid is, but unlike in Haskell, we're not only providing the operations that you have on a monoid, so the ability to combine two values and also placeholder value you can use when you have nothing to combine with anything, but also their properties. And so we saw that the binary operation is associative, meaning that it doesn't matter whether you're doing things left to right or right to left or nested in weird ways. It's all the same result. And we saw that the placeholder value is boring in the sense that if you combine it with anything else, it goes away and you only keep the other non-boring value. And then we introduced some of our favorite monoids. So we had the list monoids, where the carrier set is lists, and the way to combine two lists is just appending them side by side. And because when you're appending, you're putting the left list first and then the right list second, it doesn't really matter how you put the brackets if you're combining three lists, right? You're just going left to right through the elements of the first, the second, and the third. So that's why it's associative, which we proved in line by induction. And then we also proved that the empty list is a good notion of placeholder value for that monoid. So the empty list, if you append it on the left or on the right, it doesn't change the value overall. With the difference, of course, that because of the way AGDA works and because of our definition of append, one of the proofs is really easy. It just computes away and it's true. And the other one needs to be done by induction, but now you should be used to it. And then we saw another one, which is the monoid of endomorphisms, so endo functions. So if you have a function from a set to itself, even if the set doesn't have any structure whatsoever, that function space itself has the structure of a monoid. Why? Because if you have two functions, you can combine them by running first the first one and then the second one. And the notion of not doing anything for that combinator, so for that notion of combining two functions, is just the identity function. And then because of the way AGDA's equality checking is built, we saw that all of the proofs are trivial because the function is equal to its eta expansion. So if you remember, this is saying that f is the same as lambda x f of x. And then with this argument appearing, composition can compute, identity can compute, and you're just ending up with two things that are literally the same for all of these cases. So they're very easy to do. All right. And then we built a parameterized module. So it's a module. Maybe it's a bit weird. It's a module inside of a module, but that's not a problem in ACTA. We can just have as many nested modules as we want. And here it takes an extra argument, which is called mon, and it is an arbitrary monoid. And so it's telling you, OK, let's just assume that such a thing exists, and then we can program against it. And as I was saying yesterday, it's a good idea to always build an example of two, because you might come up with an interface you think is really useful, but then doesn't actually have any inhabitants. So if you write a ton of programs against that interface and then you can never instantiate it, you've just lost a lot of time. And then we saw that, so if you have a monoid, you have the ability to combine two values, and you can turn that into the ability to combine an arbitrary number of values. So if you have a list of them, you can just squish them together to get a single one out. And we saw that squishing commutes with appends. Ooh, actually, we could maybe prove something interesting here. Something we missed. So if we squish the empty list, we just get mempty, the placeholder value for the monoids. And that's because of the definition of squish as a fold over the input list. And if you look hard enough at these two lines, maybe you'll notice, okay, if I can scroll, that here squish is taking us from the mempty for the list monoids into the mempty for current monoid, the abstract one that was passed as an argument. And here squish append is telling us that squish takes us from the combination of two lists according to the list monoid to the combination of the two values obtained by applying squish to each one of these. So we call this a homomorphism because it's a morphism that preserves structure. So you could, here we showed it as a morphism from list of M to M, but what the properties afterwards are proving is actually a morphism from list of M seen as a monoid, so equipped with the empty list and append, into M together with its own notion of emptiness and combination. So it's very important to spot these morphisms because it's basically telling us that they are really well behaved, right? Because they are preserving structure. So if you have some results on the source, you can probably preserve them through on the output of the morphism, which we will see shortly. But before that, we need to go back to the cliffhanger. So the idea was that in CS316, you've seen not only fold R, but also fold L, which is processing not the list right to left, but left to right this time. And because a monoid is precisely a set equipped with an operation that doesn't care whether you put the parentheses to the left or to the right, we should be able to prove that the two variants are actually equivalent. So they're returning the same result. So this is what we had set up, and I said it was a bit tricky, so let's see if I can prove it. So there's only one thing in scope. Let's see, yes, okay. There's not very much we can do apart from taking it apart. And if we look at the base case, well, we have two very simple equations, expressions, we normalize them, we get the same values. So this is proven by Raffel. And then if we have squish on one side and squish prime on the other, well, what we would like to see is computation sort of popping the x's out so that we could make a recursive call saying squish on x's is equal to squish prime on x's, and then we would be golden. The problem is that the way fold L compute, if you remember, means that, so fold R will pop the value out and combine it because fold R is just using the function on the outside of the recursive call, whereas fold L is shoving the value inside the recursive call, inside the base case of the recursive call, because we have this notion of an accumulator here. And so this is where we realized that we messed up. I mean, we could try to rewrite by squish prime correct of x's, and that does make a little bit of progress. So now we have fold L here, which is squish prime, and it's squish prime because it's on mempty, but here we have fold L, but it's not on mempty anymore. And so here we could try to prove an ad hoc theorem for fold L, but that's probably not a good idea. So the general technique, and it applies every time you have a variant of an existing function that uses an accumulator to sort of store the intermediate results is to prove something that's actually more general than the statements. So how do we do that? Well, we see that in the recursive call, what changes in fold L is the notion of the accumulator. The function itself will stay the same. So we can declare an auxiliary function saying of this sort, for instance, which says, well, if the accumulator is going to vary, then I'm going to add it as an extra argument that's explicit, because then I can talk about it. Whereas here it's defaulted to empty, and once it's set to empty, we can't do anything about it. So I have the slightly more general version saying, if you give me an arbitrary accumulator, I'll compute the squish prime starting from that accumulator. So, and then you can reduce the old squish prime to saying, well, it's exactly that computation, but that we kick off with the boring accumulator. But now I can prove a theorem about the generalized version of squish prime. So what we want ultimately is something like this. Lots of noise, empty, ac prime. There we go. So what we want ultimately is something like this, but what we just saw is that this is not provable, because mempty will change into mempty with an x shoved into it at some point. So the trick then is to make this polymorphic. We're going to prove a result for any accumulator whatsoever. But now, of course, this is not true anymore, because you've kick-started the computation on the right-hand side with an arbitrary accumulator as the initial value, but on the left, you're still computing the same thing. So you need to also patch up the left sides. And if you look at the way fold L works, you can see that at any point during the computation, no, that's fold R. Can I get fold L? At any point during the computation, the accumulator will correspond to a prefix of the list we've seen. So you will have accumulated values left to right of the current point you're in the list. And so if you prove a theorem that says, well, if only I had ac already to the left of my current squish, then it would be equivalent to a squish ac prime kick-started with this accumulator, right? You've seen 1, 2, 3, and now you're going to squish 3, 4 here. Okay. And now this should be provable. Oop. So again, we introduce everything in scope. The ac is not changing. Both functions compute by induction over the list, so let's split on that. In the base case, well, it's now not provable by REFL anymore, but it looks an awful lot like one of the constraints we have for the monoids, right? We're saying if I combine ac with mempty, it better be equal to ac. And that's just this one, I think. Yes. Ooh. And now we have the step case, the one where we couldn't come up with a proof last time, and it should be a bit better. So we are combining this original ac with squish of x's. And on the other side, we're doing the same, but starting from ac. But if we normalize this, we can see that the fold R has emitted the x combined with the recursive call, so x has come out. And then here on the fold L, the x has been shoved into the accumulator. So this is not going to look great if we just do rewriting and so on. But if we do equational reasoning, we might be able to, oh no, have a nice proof. So I import equational reasoning. I open it locally. So I'm saying, okay, we're going to begin, and we have a bunch of steps. What did I do? Oh, I'm missing the last one. There we go. I'm using Control-C, Control-S to put in the start and the end. And then I want to rewrite these slightly, so I'm going to use the no proof needed kind of step, which is true by computation, but still gives us a little bit of information on what has happened. Oops, missing a hole. So I guess this one can be filled in by normalization, and then I can just refold this because it's just too noisy. I don't know why it's yellow. But this is basically the way foldar is computing, right? It's using the combine on the outside with the head and the results of calling foldar on the tail. And then on this side, well, on this side, I think it was somewhat disgusting, but let's see. It's something like that, but if we squint hard enough, we might notice that this is just a different squish arc prime, or a squish arc prime with a different accumulator on the tail. Okay, so now we need to bridge the gap between these two things. So I suppose here I already have a squish arc prime on a strictly smaller list. So I can directly invoke the induction hypothesis because it will allow me to move to arguing about squish. So let's do exactly that. If I do a recursive call here, it might even be able to, no. So the new accumulator has absorbed X, and the new tail is X's. For some reason, it doesn't want to see that. And now here, maybe I can bring these close to each other. If I don't drop half of the line, it will be better. And we can see that we are almost there. We now have the same expression, except for the bracketing. But the monoid is specifically a structure where the bracketing doesn't matter. So we can use associativity, and hopefully it's in the right direction. No, it's not, so let's just revert it. And it should prove that these things are equivalent. If I can reload, yes. So the crucial step here was really in generating this more general type. And this is a very generic pattern. Maybe I can post a link on Mattermost later with some exercises on generalizing the induction hypothesis, because this is a very common thing to do. If you're defining reverse, for instance, like the easy definition takes the head and appends it at the end of the reversed list, but that's very inefficient because append will just retraverse the thing again and again and again. Whereas if you use an accumulator, you can slowly reverse the list in just one traversal. But then to prove that it's equivalent, you will also need to have a more general statement like this, because the default one won't do. And I'm sure there are tons of other examples. And once you have your more general statements, well, why is it so slow? We should be able to, maybe I should open at the top level. Let's just look at the goal as it is. So if I try to use squish arc prime correct on the empty accumulator, which is the one we start with when we call squish prime and x's, and I look at the goal, maybe not. I can see that it's not unfolded enough. This is too unfolded, but whatever. We can see that the right-hand sides are the same. This is because squish prime was exactly defined as squish ac prime over the mempty initial accumulator. But on the left-hand side, it's not quite the same. We have the squish here and here, but we have this extra mempty at the front because we had this more general type here that was saying, well, for any accumulator, I start with it. But not to worry, we can use equational reasoning once again. Okay, this is a bit all over the place. So it's not all of these steps that do not have any justification are not strictly needed, but they just make the proof easier to read. So if you want to be kind to your future self, that's a good thing to do. Okay, that's not what I wanted. I wanted mempty here with squish x's. But okay, this one is not true just by computation. It's the one at the end that will be true just by computation. Whoop. What? It's computing too much. Okay, so this is the one that I want. So the one that I want to expose is that squish prime is defined in terms of squish ac prime. But because squish ac prime is defined in terms of fold L, if I fully normalize, everything unfolds and I'm going past my initial goal. So that's the one that I want. And this step here is exactly the more general results we had proven, right? So we can do this. And then we should have the symmetry. So let's revert that bracket. And now we have exactly the mempty equality that is given by the monoid. So that's the steps. If you try to prove this just using rewrites and so on, it's probably going to be horrible and unreadable. This is hopefully something that can be followed, like the step-by-step process. But yeah, the message is really to think about the generalization of the result that you want, to actually find the results that the statement that you need, the statement that you can get. Because what you want is sometimes a bit too precise compared to what you need. All right. And then, well, I sort of teased the fact that we're going to talk about homomorphisms. So let's just do it now. I forgot about this. So a homomorphism is, and we saw this actually there's this in the coursework also, when we are taking our representation of polynomials, right? And we are proving that addition ends with 0 and opposite forms a, what is it? It was a group, I think. It's an abelian group. And we saw that then the interpretation into an arbitrary ring was preserving the structure. So if you were doing addition on the syntax, you were obtaining the same thing. You were obtaining addition of the semantics. And these homomorphisms are a way to make this formal. So just like we had an interface to describe monoids, we can have an interface describing what it means to be a structure preserving transformation of one monoid into another. So let's do that now. So homomorphism. So I have a source and a target monoids. And yeah, that's maybe set. and I want to describe what it means to have a structure preserving function between them. Well, the first thing you need to have is actually a function, right? So let's see, I need to open monoid, I think. So to have a structure preserving transformation, you need to, first of all, have a transformation, which will take values in the source monoid and turn them into values in the carrier, in the target monoids. And then you need to prove that it's mempty respecting, or resp, I guess, which is to say that if you transform the notion of mempty from the source monoid using our mapping, then you get the notion of mempty for the target monoids. And then we need to have the combine resp, which is saying that if you take two values x and y, it doesn't matter whether you combine them and then transform the result, or you transport both of them and then combine the separate results. And this is said by stating that applying the function to the combination of x and y is the same as applying the function to x and combining it with y. Ooh, this is not going to work. Yep. Okay. Let's do what I didn't want to do, but whatever. So what's the problem? Maybe I should explain what the problem is before fixing it. So it's similar to what we saw yesterday. So I open monoid once, which means that now I have all of the projections in scope and I can apply them to each of the interfaces that I have, right? So in particular, when I'm defining the type of my function, I'm saying it's between the carrier of S and the carrier of T. So far, so good. Then I'm saying mempty respecting between the mempty of S and the mempty of T. The problem now is that this combine function is infix, but because I've not applied the monoid module to a specific monoid, it now takes three arguments. It takes the monoid and then two values belonging to it, which means that it's not quite infix anymore. It's just somewhat nasty. So the fix for that is to actually name the two separate instances. So this is saying it's a bit convoluted because it's involving different scopes and different objects. But this is saying I'm defining a module, S, and it contains all of the characterizing fields of the monoid S, which I took as an argument. So this is monoid the record, this is monoid the module, and then I'm defining T as containing all of the fields in the monoid T. And because these are modules, then I can use them to qualify the names that are in scope. So instead of talking about the carrier of S, I can say the carrier that's stored in the module S, which is now containing all of the content of this S monoid. So it's a bit technical, but it's basically declaring names for all of these values. And because now I have separate names for the mempty of one and the mempty of other, rather than projecting mempty out of one or the other, I also have different names for this thing. And because qualifying works on infix names, I'm now saved and I can actually write this the nice way. Right, so to recapitulate, a homomorphism is a morphism, so it's transforming values into values that respects the structure. And we did mention a couple of these. So let's see, there should be one homomorphism list. So for an arbitrary monoid, there should be a homomorphism between the list's monoid, I think we had called it like that, and M. Yes. And here we need a carrier. So if you remember the list monoids, well, it's what we call the free monoids because it doesn't assume anything on its input set. And no matter what the structure here is, it will give you a monoid, guaranteed. So it's taking a set, and I'm extracting the carrier set of the monoid. And so now I should be able to define this thing. We're using the observation that we made earlier, right? If I normalize this type, it looks a lot simpler, and it's actually the type of squish. Monproof squish over M. So just to replay that, we asked for a function between the carrier of the list monoid built on top of whatever the carrier of M itself is into M. And if we normalize everything, it doesn't want to normalize. If we normalize everything, it means that we want a function from list of M to M. And this is exactly the type of squish that we had defined, which is why it fits in the whole. And then the fact that it respects the placeholder value that we use, mempty. So this is not super readable, but it's saying that squish applied to the mempty for list, which is to say the empty list, is equal to the mempty for M. And if we normalize again, this time from the first time, it's true by construction of squish. And I think we actually call this squish mempty M. And finally, the appends results. So if we squish together two values combined using the notion of combination for the list monoid, we should get the same as squishing the first, squishing the second, and then combining them in the target monoid. And this is, again, well, if I normalize it, it gets a bit clearer, and its squish of append is combination of squishes. So you have to squint to really see what's going on. But what? Oh, it's because I was silly and I was taking these arguments implicitly. It's a bit of a heuristic to know whether you want to take the arguments implicitly or explicitly. The fact that we had to introduce them explicitly to split on them and then for the recursive call was actually a very good sign that it was a really bad idea to leave them implicit. And now, no, it should work. Okay, but what's the point of this? Well, like with any other interface, I showed you that we could program generically against a monoid. We can also program generically against a bunch of monoids and homomorphisms between them, which means that you can prove the result once at the highest level of generality, and then whenever you need to deploy it in various scenarios, instead of redoing the proofs from scratch, you can just use the work you've already done. So in a sense, these parameterized modules are extremely powerful because they give you sort of the same generality that you get with Haskell type classes, except that here you're never relying on them being filled automatically, so there can be ambiguity. In Haskell, you can have at most one instance for every type. Here you can have just as many as you want. And it's a good thing because if you think a little bit about it, if you look at the Booleans, for instance, there's tons of monoids on them, right? There's the one for disjunction, for conjunction, for XOR, for, I don't want to say anything stupid, I think, is that it? Maybe there are more. Well, at least these three ones are monoids. If you were forced to pick your favorite one and then you couldn't deploy the results for any of the other ones, it would be a problem. So here we have the power of type classes, but with the flexibility of picking whatever instance you want, depending on the task at hand. And then I think I'll go to defining the last thing for today. So monoids are a very good thing to start with because they are very simple. Well, okay, the types can get a bit disgusting already, but conceptually they're very simple, right? You have a single set, you know that you have a value in it, and you have a binary operation. But generally, when we're thinking of objects that we're manipulating in mathematics, it's quite rare that they're all living in exactly the same set. I mean, for the base types, sure it works, but then after a while it doesn't. So for instance, at some points in the courseworks, we are looking at proofs that m is less than n. And if you think about it, m is less than itself, is less or equal to itself. So that's sort of a dummy value, right? That doesn't contain any interesting information in it. And then if you know that m is less than n and n is less than p, you can combine the two proofs so that you get a proof that m is less than p. So you again have a similar structure, except that the dummy value is now indexed by something extra, and the composition now needs to be sort of type aligned in the middle. And you're not just combining, it's not just limited to values anymore, now it's also arbitrary functions, right? Or proofs or whatever. And the notion behind the structure, which is just a fancy monoid, is the notion of a category. So let's just copy paste the definition of monoids, and then maybe we can say something about a category. So similarly, it's going to be a large set because we're going to be talking about some objects, and the objects will themselves be a set. So let me just comment this out. Just we're keeping it in mind. Right, so we have not only objects, but now if you have this example of, so example less than. So the objects here are the natural numbers because you're talking about m being less than n, etc. And then you have function or morphisms behind them. They're not quite functions. They're something that takes a source and a target, both of which are objects, and just give you a set. So this is describing all of the ways you can turn the source into the target. You might have 0 of them, you might have 1 of them, you might have very many of them. So that's taking care of our carrier here. And then we need a way to combine things. And as I was saying, the notion of combination here that we have is, for instance, if I know that m is less than n and n is less than p, then m is less than p. So the combination, which I'm going to pointedly call composition, is taking, well, for any three objects, source, middle, targets, if I can go, or maybe this is a bad name, well, whatever. Let's do then. If I can go from the source to the middle, and I can go from the middle to the target, then I have a way of going to the source to the from the source to the target. And this is abstracting away this idea of, well, I guess I can say source is less than middle, can't spell, is less than target, therefore source is less than target. Okay, and then we have a way of not doing anything interesting, which again is a great way to kickstart a computation. Okay, exactly what I was fearing would happen. Right, so that's taking care of the types and operation aspect of it. So it's a bit like a monoid, except that now you're starting from somewhere and you're ending up somewhere else. But we would again like to have some properties, and luckily for us, the properties that we had for the monoid still make sense, right? So them, will they type check? Probably not. I will need to add some annotations, but the ideas, the core ideas are still working. Yeah, that should be fine. So then ASOC. So this is morphism source middle 1. Then I can go from middle 1 to middle 2. And finally, I go from middle 2 to the target. And I will need to say that all of these exist somehow. Let me comment this out. And I called it then here. Right, so this is more exactly the same as the monoid, and what it's telling you is that it doesn't matter which path you're taking to go from the source to the target, as long as the individual bits of the path you're following are all the same. So you could describe your path as first going to the first step, and then going to another one, and then to another one, or first going 2 steps to immediately and then to the last one. And the two trips should be equivalent. And we have the same thing for identity then, or then identity, I suppose. So this is saying no matter what the source and the target are, if you know how to go from the source to the target, going there and then staying in place is the same as simply going there. Oop. And intuitively, if you're thinking in terms of paths, it also makes sense, right? And then we also have identity then, which is just the other side of it. So if you know how to go from the source to the target, and you start by staying in place before moving from the source to the target, it's the same as moving immediately. And I think I will stop there. You can maybe try, well, okay, so the boring thing to do, of course, is to just prove that this is an instance of it, but you can maybe try to think of a more interesting, different instance of a category. Or maybe a generic program you could write against a category. So we had squish, which is taking a list of values and concatenating all of them into a single one. Maybe you can take a very long path of individual steps, all of which are sort of typo lines in between, and just squish them into a single morphism from the source to the target, not talking about anything in the middle. All right.